Okay, welcome to the video. So today we're going to be going over the third video in the regression using R series, and that's going to be adding categorical predictors to a regression model. And so before, in our earlier videos, we looked at how to do simple bivariate regression with just one predictor. Then we moved on to multiple regression, and now we're going to talk about how we might add categorical predictors. And in the next videos, we'll go over how to mean center predictors and adding interaction terms. And as a note, as we've previously done with our videos, the first portion of this video will be going over how to run the code, and then the second portion of the video will be going over how to interpret and report the results. So when I'm running the code, don't worry if you're not sure how to interpret some of the things you see. We'll go over that in the second portion of the same video. Okay, and so we will go ahead and get started. And so we're going to be using the same data set that we've been using. And this is the prediction of turnover intentions or employees' desire to leave from a variety of different variables. And as always, the link to the original data set and then the version that I'm using is the links are provided here. And you can find this on my GitHub page, which is also linked in the description as well. And so to get started, we'll go ahead and load these packages. We won't need all of them for today, but they're the same packages we've been using, so better just to go ahead and load them. If you don't have them, of course, you'll have to install them. Okay, and I'm going to go ahead and load our data set. So as you can see, this is our data set, and here is our outcome measure, turnover intentions. It's measured on a 1 to 5 scale, where 5 means they are strongly thinking of quitting. And then we have our predictors, so age, gender. We have centered versions and raw versions of all of our variables. Don't worry about the center versions for now. We'll go over that in our next video on how to use mean-centered predictors. For now, we'll just be using the raw predictors. And one thing I wanted to point out is if we look at gender, for example, this gender raw, we see that it's coded numerically as 0, 1. So we need to tell R that this is not a numeric variable. Because if we come down here and we type in class dat1 gender raw, it thinks that it's numeric. So we need to come back to our code after we load our data set, and we need to convert all of our categorical variables that are coded with numbers to factors. So R knows that these are, categorical variables and not numeric variables. So all you do is you type in the variable that you want to change. You say as factor, or you can just type in factor. Either one's fine. And then we'll type in the variable. So again, we are changing the dat1 data set and the gender-centered variable to be a categorical version of this same variable. And again, we're going to be working with the raw versions, but I'm going to go ahead and do this for all of my categorical variables. And then the next thing we'll do is we'll specify what we want the levels to be. So whatever your group is that's coded as a 0, you need to specify that first. So for me, men were coded as 0, women were coded as 1, and so that's why I've specified that the levels of my new variable are going to be men, comma, women. So we'll go ahead and run all of this for all of our categorical variables. And then it's always a good idea to check and make sure that the variables are as they should. And coming down here to the bottom, now we see that these variables are showing up as factors, and we see that the levels, are shown as well. Okay, and so now we're going to scroll down to the adding categorical predictors portion of our code and our syntax. And as usual, this can be found on my GitHub page. And so for the first example, we're going to look at just using one single categorical predictor. So it's going to be turnover predicted from manager status, which is whether or not the employee is a manager. And so we can take a look at our descriptive statistics just to get started. And so we're going to look at turnover levels by manager status. And here we see that it looks like the mean turnover levels for our non-managers and our managers are pretty similar. And again, we can tell that from down here. And then we can look and see that the skew and kurtosis levels of turnover intentions by level of our categorical variable, they seem to be within reason. So you want to make sure that if you're going to be running a regression model, that your data isn't overly skewed or kurtotic, both overall and then also by different levels of a group if you're going to be using a grouping variable. And so we also might want to take a look at just a side-by-side box plot of turnover intentions by manager status. So this would be a side-by-side box plot of your outcome measure by your grouping variable. So we'll use ggplot. This will put our data set here. This is where we specify our x variable, or our grouping variable in this case, which is manager status. This is where we specify our outcome measure. And then I want the color of my box plots to vary by manager status, and I want them to be filled in with a color that varies by manager status. And then this alpha equals 0.3, that's just a style thing. It's just to make the plots transparent. You'll see in just a second. So I'll come down here, I'll click zoom. And so as we can see, we have a side-by-side box plot. And this is what I meant by transparent. You know, if I hadn't specified alpha equals 0.3, this would have been perfectly fine. It just would have been solid instead of this kind of like see-through color. I just like it visually a little better. And so again, this is just a box plot of turnover intentions for the managers and the non-managers side by side. And now we'll go ahead and fit our regression model. So our outcome measure, tilde, our grouping variable, manager status, and then data equals dat1. We might want to check and make sure that our contrasts or our dummy coding is as we expect it to be. And so the easiest way for me to explain this is just to go ahead and run this line of code. And then down here, this shows us what our reference group is. So the non-managers are our reference group. They're coded as 0, and the managers are coded as 1. And so that's just helpful just to confirm that you know which group is going to be your baseline group or your reference group, and which group is coded as your comparison group. And this is especially useful when you have more than 2 levels, like we'll see with some of our variables after this. So let's go ahead and take a look at our model summary. I'll make this a little bigger. And again, we'll go over the interpretation in a minute, but this is the regression model predicting turnover from manager status. And we see our estimates. We have our intercept estimate and then our slope estimate. And this is the slope for predicting turnover intentions when we, for manager status, when we go from the non-manager group to the yes manager group or the manager status. And then this is where we can see whether or not the coefficients are significant, specifically if they're significantly different from 0. Of course, our intercept, that's pretty meaningless, and then we see that our slope for manager status is actually non-significant. And again, we'll go over the interpretation in a minute. Okay, so we'll go ahead and talk about how to interpret this first model. And so what we see here is this is the same box plot as before, except now I've just added the ability to see the individual data points. And I've also drawn the means for each level, so the mean turnover intention levels for the non-managers and the managers, with a line connecting them. This just helps us visualize whether or not there's a mean difference in our outcome variable turnover intentions by manager status. And as we can see, there doesn't appear to be much of a difference at all. The managers have slightly lower average turnover intention levels than the non-managers, but it's not a significant difference. And so here I came in and I filled in the information from before, and we'll talk about just the regression, the raw regression slope first, and then we'll go back and I'll show you how to get the standardized coefficients and the confidence intervals. I just wanted to explain what we're looking at with our regression slope, our raw slope. And so from our model, our intercept was 2.14 and our manager status was negative 0.09. And so what this is showing us, sorry, I went one step too far. Back to our regression model output for turnover predicted from just manager status. What this is showing us for our raw slope, our unstandardized slope, is that the intercept tells us the predicted level of turnover intentions for non-managers, and then the slope tells us, for manager status, tells us that switching from a non-manager to a manager gives us a change in predicted average turnover intentions of negative 0.09. And sure enough, as we look at the mean turnover intention levels down here for our non-managers, the mean is 2.14, and then for the managers, that average turnover level is 2.05, and so that difference is 2.14 minus 2.05, Well, that's 0.09. So what I'm getting at here is that when all we have is a single categorical predictor with 2 levels, this is absolutely equivalent to just doing a t-test on the differences in turnover intentions between our non-managers and our managers, right? So running a regression model with one categorical predictor that just has 2 levels is absolutely equivalent to running a t-test on the same variables. And then coming back to our code real quick, again, sorry I jumped around, I just wanted to make sure that we understood what we were looking at. This is how we can get a confidence interval for the raw slope, the unstandardized slope. So we just do conf_int and then our model. And here's our confidence interval. And then because this is a non-significant predictor, we see that this confidence interval includes 0. That's another way that you can tell whether or not your predictor is significant by looking at the confidence interval to see if it includes 0 or it doesn't include 0. And so now we can get our standardized slope and confidence interval by doing effect size and then our model. And here is our standardized slope estimate and the confidence interval. So now we'll go back to our PowerPoint and talk about how to interpret those real quick. And so again, here we have our beta weights, which is just our standardized regression coefficients, and I just got this from the information that we just looked at. And the point estimate for that standardized slope is -0.10. And so the interpretation is that switching from a non-manager to a manager gives us an expected change in turnover status, or sorry, in turnover intentions of -0.1 standard deviations this time. And then as we look at our p-value, the p-value is 0.11, and again that's non-significant at the 0.005 criterion level. And then here's our confidence interval for our standardized slope. And again, as I mentioned, this also includes 0, which backs up the fact that our p-value was not significant. And then our r-squared shows that less than 1% of the variation in turnover intentions is explained by manager status. Actually, less than 0.1% of the variation in turnover intentions is explained by manager status. And again, that makes sense because it was a non-significant predictor. Okay, for the next portion, we're going to take a look at how to do how to do regression where we have a categorical predictor with more than 2 groups or factor levels. So we still only have a single categorical predictor, but now we have more than 2 levels. So instead of just yes, no, manager, non-manager, we're going to look at education level, which actually has 7 different education levels. Well, really 8, because the base level, 0, which is coded as 0, is actually folks that do not have a college education. So we'll go ahead and fit our regression model, and so we're going to call it model M3B, and then we're going to do LM, and then our outcome measure, tilde, our categorical X variable, and that's going to be education level this time, and then our data set is still DAT1. We'll fit our model, and now I'll explain to you what I meant when I stumbled a second ago and was trying to describe how this was coded. So we'll do contrasts and then the education variable, and then if we come down here, what I was trying to get at is that there are 8 different education levels, but the 0th level is our reference group, and this is the folks that do not have a college education, and then this is the number of years of college they've attended, and each year is coded as a different factor level. So our reference group are the folks that have never been to college, and then we have a dummy coding system where each additional year is coded as a comparison group. And so all of our comparisons are going to be made relative to this baseline group of non-college. And that'll make a little bit more sense when I explain the model summary. So let's go ahead and take a look at our summary. I'll make this a little bigger. And so what we can see here is that now we have a slope for each of the 7 years of college education, and then our intercept, which is our baseline, this is actually the estimated turnover intention level for the folks that have not been to college, which is our baseline group. And then the rest of these are the slopes for each of the individual levels of college education, number of years in this instance. And these are all slopes that are compared to the baseline. So for example, this negative 0.77 for education 1, this is compared to the folks that don't have any education. And then similarly, if we go all the way down to the last one, to the education level 7, this is the average turnover intentions compared to, again, the same reference group of the folks that have not been to college, level 0. And so don't get confused and think that these slopes are compared to like one another. So for example, don't think that like the slope for education level 1 is compared to 0, but then that the slope for 2 is compared to 1. It's not sequential. These are all referenced in comparison to your baseline or your reference group, which for us, again, as we saw when we look at our contrasts, that is the education level of 0. So just be careful about that. And then we can also get descriptive statistics. So we're going to look at turnover intention by education level. So our variable of interest turnover grouped by education status. And so what I want to explain really quickly is let's look at the education, the mean education for the folks that are in education level 7. They have a mean turnover intention level of 2.0. Well, if we come up here to look at the folks in group 0, which are the folks that have no college education, their average turnover intention level is 2.83. So again, 2.83 for the 0 group, 2.0 for the 7 group. Well, if we go back to our model summary, this actually makes sense because look at the slope for education level 7. It's negative 0.83, and that's just coming from the average turnover intention level for our reference group, which was 2.83, minus, or the change in turnover intentions as you transition from that reference group of 0 to the level 7, and their average was 2.0. So 2.83 minus 2.0, yep, slope is 0.83. So again, our slope is just the difference in our outcome measure, our average outcome measure between each of these different groups and the baseline group. Now it might be the case that we want to re-level our factor to change the reference group. So in the example we looked at above, the reference group is education level 0, no college degree. Well, we can re-level this to make year 7 be the reference group. And so by default, R will set things up dummy coded so that your lowest group is the reference group, right? Whichever one comes first. So if you want to change this, it's actually really simple. You can just do the variable that you're interested in, your categorical variable, and then re-level, and then put the name of the variable and change it to the reference group that you want it to be. So if I want to make year 7 be the reference group, or education level 7 be the reference group instead, I'll just run this code. I'll check the contrasts to check the dummy coding again. And now we see up at the top our first row with all the zeros indicating that it's the reference group. That's level 7. So really, really simple. And then we can run a regression model with our variable. Now that it's been re-leveled, we'll look at our model summary. And sure enough, now the intercept is 2.0. Well, if we go back to our descriptive statistics from before, that 2.0, that's just the mean turnover intention level for group 7. So again, they have now been made so that they are the baseline, and that corresponds to the intercept in this example where we only have just the single categorical predictor. So again, all this did was we changed our reference to be 0 to now be 7. And then we can re-level it back, so we'll go ahead and set it back to reference group of 0. And we'll double check to make sure it was successful. Yep, and then again we see now group 0 is the one with all the zeros now, as it should be. So moving on, now we're going to look at how to include a categorical variable but still keep a continuous predictor as well. And so now we're going to predict turnover from pay satisfaction and manager status. So instead of just having the categorical variable, now we're going to look at how to do this when we also have a continuous predictor, so multiple regression, basically. And so we'll start by getting a scatter plot. And what I'm going to actually do is I'm going to get a scatter plot of both predictors. And so the first thing right here, this is our data set as usual. This is going to be our continuous X predictor, so pay satisfaction in this instance. This will be where you put your outcome measure, but we're going to color it by our grouping variable, which is manager status. And then we come down here, and this geom point is what makes it a scatter plot, and then this geom smooth adds a regression line. So again, the only thing that you would need to change is your data frame, of course. This is where your continuous predictor would go, and this is where your outcome measure would go, and then you want to color it such that it corresponds to your categorical or your grouping variable. And so we'll zoom in, and so what we have here is we see turnover on the y-axis, pay satisfaction on the x-axis, and then we have a different regression line for the managers and the non-managers. And so what we can see here is that this is really pretty much super similar, with a slight difference where the regression line for the non-managers is higher than that for the managers. But the slope of this regression line is parallel. And what this would suggest is that the slopes are the same for predicting turnover intentions and pay satisfaction for the managers and non-managers, right? There's not an interaction between manager status and pay satisfaction. And we'll talk about that more in the interactions video. I just wanted to point out that we can see this slight separation, this vertical separation between the managers and non-managers, but it's very, very slight. There's practically no difference, which makes sense with what we've seen before. And so another way to put this is now we're looking at turnover status predicted from pay satisfaction controlling for manager status. Or alternatively, turnover status predicted from, turnover intention predicted from manager status controlling for pay satisfaction. Either of those verbalizations would be fine. It just depends on what you're interested in. And so we'll come down here and we'll fit our regression model. So turnover tilde, pay satisfaction, and manager status. We'll get the summary of our model. And then as always, here's the estimates of our intercept and slopes. And I'll talk about the interpretation of those in a minute. And then here's the significance test of those slopes. We can get a confidence interval for the unstandardized slopes. And then we can get an effect size, use the effect size function to get the standardized slope estimate and confidence interval. And there it is. And again, we'll go over the interpretation of these in just a minute. We might also want to get our effect size estimates, the squared semi-partial correlation coefficients. And so we need to do this slightly differently than how I showed it in the previous video. I would honestly use this method just every time you want to get semi-partials, even if you don't have categorical predictors. So you can just do this pretty much any time that you're interested in getting squared semi-partials, regardless of what type of regression you're running. And so what we do is we create an object. I called it AOV M3C because M3C is my model, but you can call it whatever you want. You can call it Bob for all you want. But you need to specify the ANOVA function, and this is where you put in your regression model, and this is where you state that you want type 3 sums of squares. I'll make another video going over the differences, but for now, this is what I recommend. And again, the only thing you need to do is come up with a name for this object you're creating, and then use the ANOVA function where you put in the name of your regression model, and then put type equals 3. So we'll do that. And now we see up in our environment in the top right, this new object, it's an ANOVA object, and now we can run ETA underscore squared at a squared for this object, and then we'll say partial equals false because we want semi-partials, not partials. By default, it will give you partial or squared partial correlations. So we're going to say partial equals false to get the squared semi-partials. And then here we have the estimates right here and their confidence intervals. And again, we'll interpret this in just a minute. One other thing we can do is we can look at whether or not our categorical variable predicts our outcome measure above and beyond the continuous measure. And we talked about nested comparisons or hierarchical comparisons previously, and it's the same thing as before. We just do ANOVA and then our current model, which contains both manager status and pay satisfaction, and then we'll compare it to M1, and we'll go back up to our original simple regression so I can show you what M1 was if you weren't with us previously. There it is. And so what M1 is that's just turnover predicted from pay satisfaction. So we'll go ahead and run that, and then we'll come back down to where we were. Here it is. Okay, yeah. And so again, we are comparing these two models, one that has both turnover intentions and manager status, and one that just has, I apologize, one that has manager status and pay satisfaction, and one that just has pay satisfaction. And we're trying to see if adding manager status to the model that previously only included pay satisfaction improves our model fit. In other words, we're trying to see if manager status predicts turnover intentions above and beyond pay satisfaction. So you just do ANOVA and then the two models you're comparing. And then down here we can see it runs an F-test on the change in the residual sums of squares. So basically it's looking to see if you have a significant reduction in error when you add this predictor. And we can see right here it's non-significant. So in other words, adding manager status to the model does not significantly reduce error or explain variation in turnover intentions. So manager status does not predict turnover above and beyond pay satisfaction. Then we can also run what's called a dominance analysis. This really isn't necessary for a situation where you only have two predictors, but I'll show you how you would perform it. This is kind of like the relative weights analysis that we looked at previously, and the basic idea is that you're trying to see, okay, out of the variation in turnover intentions that our model explains, what proportion is due to each individual predictor. So it's a measure of what we call relative importance. It tries to tell us which predictor is more important in explaining our outcome measure. And so you just make this object DA M3C, you can call it whatever you want, and then do dominance analysis with your model inside. Then we'll print the results, and we can see down here at the bottom the average contribution to our model to explaining our outcome measure, turnover intentions. We see pay satisfaction dwarfs manager status. There's a huge difference. And then we have our regression diagnostics, so we're going to check the assumptions that we make, and again I'll go over the interpretation of this later. We can do plot, and then we need to come down here and put in our cursor to hit enter. And so we see our different regression diagnostic plots, and this is just the base R version, where again all you have to do is specify plot and the name of your model, and then come down here and press enter to go through. You can also do ask equals false so that you get them all at once. Let me clear this so you can get a better idea. Yeah, and so when you do that, you don't have to come down there and press enter, so that's probably easier. And then if we want to get a prettier version of the same plot with a few extras, we can run these, and again, each of these lines of code, you're just putting in the name of your model. And so we see the different diagnostic plots. And as usual, we'll interpret those in just a minute. So that's how to run the code, and now let's take a look at what all this means. Okay, so coming back to our PowerPoint, we have we already talked about predicting turnover from just a single categorical variable and how to interpret that. So now we'll talk about the multiple regression, where we had turnover predicted from both pay satisfaction and manager status. And so this is just that same scatter plot we saw from before. And now we'll talk about the results. And so again, I got all of this information in this chart from the model summary and the output that we looked at in R. So that's where these numbers came from. And this is how I like to display my results. It just makes it a lot easier than trying to write these complicated write-ups, I think. And so we'll start with this column with our raw slopes or unstandardized slopes. So this intercept, this tells us that the intercept is 3.51, and then this is the unstandardized slope for pay satisfaction, for the unstandardized slope for manager status, and then these are the standardized slopes. This is the p-value for the significance test, This is the confidence interval for the standardized slopes. So again, this is our point estimate. This is the confidence interval. This is our semi-partial squared correlation coefficient. And then this is the dominance analysis. And then this is our multiple R squared. So the interpretations of these, we'll start with our intercept. The predicted level of turnover intentions for non-managers with 0 pay satisfaction is 3.51. And again, the way we know this is because the intercept is your predicted outcome level when all of your predictors are set to 0. So in this instance, the 0 for manager status, that's the non-managers, right? So it's whatever your reference group is. For the education example, it would be the predicted level of turnover intentions for people without college degrees and 0 pay satisfaction. So the interpretation of the intercept is always relative to your baseline group whenever you have categorical predictors. And then for the slopes, for every 1 unit increase in pay satisfaction, turnover intention is predicted to decrease by 0.41 units, controlling for manager status. Another way of saying this that I like a little better is if we compare employees who have the same manager status but who differ by 1 unit on pay satisfaction, we would expect a difference in turnover intentions of 0.41 units. So whatever your categorical variable is, the slope of your other continuous variable is going to be interpreted as, for every 1 unit increase in this continuous predictor, your outcome measure is predicted to decrease by 0.41 units, controlling for your categorical variable level. And then for the slope for manager status, we could say comparing employees who have the same pay satisfaction, so controlling for pay satisfaction this time, we would expect a difference in turnover intentions between managers and non-managers of negative 0.05 units. So again, the difference between managers and non-managers with respect to turnover intentions when we control for pay satisfaction is only 0.05. And the slope is not significant in this case. For the standardized slopes, our interpretation is for every 1 standard deviation increase in pay satisfaction, turnover intentions are predicted to decrease by 0.34 standard deviations when controlling for manager status. So again, that's our standardized slope for pay satisfaction. Now for manager status, the standardized slope doesn't make any difference. Doesn't make any sense. Not doesn't make any difference. It doesn't make any sense because, again, the interpretation would be for every 1 standard deviation increase in manager status. That's pretty meaningless unless we standardize our variables, and then we can really just interpret it as the difference between manager status and non-manager status. But anyways, not super important. So of all the variation in turnover intentions, about 11% or 11.5% is uniquely explained by pay satisfaction, and less than 0.01% is uniquely explained by manager status. And that's our semi-partial squared. So again, the interpretation of our semi-partial squared is we're saying out of all the variation in our outcome measure that's explained by our predictor, out of all of the variation in our outcome measure, how much is uniquely explained by each predictor. So again, just to be clear, sorry about that confusion, the semi-partial squared interpretation is out of all of the variation in turnover intentions overall, what percent is uniquely explained by pay satisfaction and what percent is uniquely explained by manager status. So another way to think about that is it tells us the reduction in error we get from adding each of these predictors to the model that doesn't include them. So in other words, if we only have pay satisfaction, well, if we add manager status, we get a pretty much insignificant reduction in error. Whereas if we have a model that only includes manager status, adding pay satisfaction gives us about an 11% reduction in error. So again, it's the amount of your overall variation in your outcome measure that's uniquely explained by each predictor, and that's your semi-partial squared. And then the dominance analysis results in this column, they confirm that pay satisfaction has a drastically greater relative importance, and roughly 11.6% of the variation in turnover intentions can be explained by the model including these 2 predictors. And I want to clarify in something I said. I probably shouldn't have said that the standardized coefficient for manager status is nonsensical. I'll go ahead and change that in the PowerPoint. So the way you would interpret that is you would say, for every 1 standard deviation increase in manager status, turnover intentions are predicted to decrease by 0.05 standard deviations when controlling for pay satisfaction. So that's how you would interpret the standardized coefficient for manager status. The reason I said it was nonsensical is because it's kind of hard to think about 1 standard deviation changes in manager status, but you can just think about it as the change in manager status, the change in turnover intentions when you're switching between managers and non-managers, controlling for pay satisfaction, but this time in standard deviation units. So I probably shouldn't have said that it's nonsensical, because technically you can't interpret it. Okay, and coming to our regression diagnostics. So turnover predicted from pay satisfaction and manager status. Again, our assumptions for regression are that our errors are independent and normally distributed around a mean of 0 with constant error variance. We also say homogeneity of error variance, or homoscedasticity, but easier just to say constant error variance. So basically what we're saying is that our assumption is that at the population level, the errors from this regression are distributed normally around a mean of 0 with constant error variance. Now, in our sample level, we only have residuals, so we examine our residual plots to see whether or not those are reasonable assumptions. And so this first thing is a histogram of our residuals, and so we're looking to see if they're distributed normally around 0, which they appear to be for the most part. And then this QQ plot down here, it's pretty much showing the same thing, just in a different format. Ideally, we'd like to see our residuals flush against this red line, indicating that they're perfectly normally distributed around 0, but this isn't too bad, except as we get towards the more extreme ends, it looks like they start to deviate more and more away from normal distribution, but overall not too bad. This plot over here in the top right, this is how we can evaluate our constant error variance, and what we're looking for is to see this vertical spread of our residuals, whether or not it's constant across our different levels of fitted values. So in other words, as we proceed from left to right, we're looking to see whether or not the vertical spread is constant. For the most part, it's decent, except for once we get down to our lower fitted values or our lower predicted values, and it looks like we don't have as much, or we don't have this constant error variance. Part of this could be because our data is only measured on a scale of 1 to 5 for our outcome measure. So, as we proceed to these lower levels, it becomes less and less, reasonable to have like predicted levels that are below 1, because it only ranges from 1 to 5. So, anyways, for the most part, again, with this plot here, you're just looking to see, ideally, you don't want there to be any pattern, so you wouldn't want this slope, and you want this this vertical spread to be constant across your residual across your fitted values rather. And then down here, this is a plot for outlier status or potential outliers. There's many different ways to measure whether something's an outlier. This uses the studentized residuals or the deleted studentized residuals. It's too complicated for me to get into in this particular video. I might do one in the future, but basically you're looking to see whether or not these studentized residuals are outside of these red lines, which mark an absolute value of 3. So ideally you don't want any of your deleted studentized residuals to fall or exceed the absolute value of 3 that's marked by these red lines, and all of ours look like they do fall within the absolute value of 3, so plus or minus 3 standardized or studentized residuals. So again, this is just one measure of outlier status. There's many different other ones, and I'll probably have to make a separate video for outliers in the future. But again, these are the plots that I would look at when I'm looking at my regression diagnostics. And it does look that while we don't have, like, everything's not perfect, it looks like for the most part our assumptions are relatively reasonable. And if they're not, so if you think that it's safe to say that your assumptions are violated. So say, for example, our residuals weren't even close to being normally distributed, or we had like a curvy pattern, some type of pattern with our residuals. Well, in that case, your coefficients, your estimates for your slopes, those aren't going to change, right? They're not going to be wrong, but the standard error can be biased, which means that your significance test results can be biased. And so the estimates themselves aren't problematic, but your significance tests on those regression coefficients are going to potentially be biased if your assumptions are violated. And so that's pretty much it for this video. We've covered how to look at a single categorical predictor. We've talked about how to re-level the levels of our categorical predictors. And we've talked about how to look at a multiple regression model where we have continuous and categorical predictors. And then in our future video, we will go over mean centering predictors next, and then we'll also talk about interaction terms. So, for example, in this current one, we might talk about how to run a regression where pay satisfaction and manager status might actually have an interaction such that pay satisfaction, the slope depends upon whether or not someone's a manager. But again, we'll go over that in the future video. I just wanted to give you an indication of another level of interpretation we can have with categorical predictors, but we'll talk about that in the future. So thanks for watching this video, and as always, the code can be found on my GitHub page, and thanks for watching. Have a great day.